Organic Chemistry, Chapter Organometallic Compounds. 2.1 Introduction. Organic compounds in which a metal atom is linked directly to a carbon atom are called organometallic compounds. A large number of metals, for example lithium, sodium, magnesium, zinc, mercury, lead, cadmium, etc., form such compounds. The organic part is generally an alkyl, alkenyl, alkynyl, or an aryl group. They are named simply by adding the name of the metal to the name of the organic group linked to the metal. For example, methyl lithium, ethyl magnesium, and butyl lithium, diethyl mercury, tetraethyl lead, phenyl lithium, dimethyl cadmium, diethyl zinc. The carbon metal bond in organometallic compounds differ widely, varying from bonds which are essentially ionic to those which are largely covalent. Thus, the extent of the ionic or polar character of the bond is largely determined by the electropositive nature of the metal. More electropositive the metal, more is the ionic character of the carbon metal bond. In general, the ionic character of the carbon metal bond follows the sequence carbon potassium, carbon sodium, carbon lithium, carbon magnesium, carbon aluminium, carbon zinc, carbon cadmium, carbon mercury. The reactivity of the organometallic compounds also depend upon the nature of carbon metal bond. Generally, the larger the ionic character of the carbon metal bond, more reactive is the organometallic compound. However, compounds having intermediate ionic character are of greater importance because of their lower reactivity and selective nature of their reactions. Organometallic compounds are extremely useful for the synthesis of a vast variety of organic compounds. Apart from these, many of the organometallic compounds are commercially important as well. For example, tetraethyl lead is extensively employed as an anti-knock compound. Organotin compounds are used as antioxidants in rubber products. Phenyl mercuric acetate is used as a fungicide and disinfectant, and organoarsenic compounds are used in medicines. 2.2 Organomagnesium compounds Grignard reagents. Organomagnesium halides are extremely important reagent in synthetic organic chemistry. These reagents are commonly known as Grignard reagents after the name of the discoverer Victor Grignard, who received the Nobel Prize in Chemistry in 1912 for this discovery. The general formula of Grignard reagent is RMgX or ARMgX, where R represents an alkyl group and AR represents an aryl group. 2.2.1 Preparation. Grignard reagents are prepared in the laboratory by the action of an alkyl or an aryl halide on magnesium metal in dry ether. Rx plus Mg in dry ether gives RMgX, that is alkyl magnesium halide. Methyl iodide plus magnesium in dry ether gives methyl magnesium iodide. Ethyl bromide plus magnesium in dry ether give ethyl magnesium bromide. Besides ether, tetrahydrofuran, dioxane, diethoxyethane or dimethyl ether of diethylene glycol, tertiary amine, etc. can also be used as solvent. In fact, THF is considered to be the best solvent since it increases the reactivity of an alkyl or aryl halide towards magnesium. It is because of this reason that the Grignard reagents of less reactive aryl and vinyl halides are prepared in THF. Like chlorobenzene plus magnesium in THF give phenyl magnesium chloride. Vinyl chloride plus magnesium in THF and heat gives vinyl magnesium chloride. Further, it has been found that for a given alkyl group, the age of formation of Grignard reagent is of the order iodide, bromide, chloride. The alkyl or aryl magnesium fluorides are, however, unknown. For a given halogen atom, the order of reactivity is CH3x, C2H5x, C3H7x, etc. That is, the formation of Grignard reagent becomes increasingly difficult with increase in the number of carbon atoms in the alkyl group. The use of tertiary alkyl iodides is avoided since they readily lose a molecule of hydrogen iodide to form an alkene. Tertiary alkyl chlorides may then be used. Procedure for the preparation of Grignard reagents. Alkyl or aryl halide is added slowly to a perfectly clean and dry flask containing dry magnesium turnings covered by a layer of absolutely dry ether or THF. The reaction mixture is warm a little when an exothermic reaction should soon start. If the reaction does not start within 5 minutes, a few crystals of iodine are added and the reaction mixture is warmed a little. A vigorous reaction soon sets in and magnesium gradually dissolves, forming a cloudy solution of the Grignard reagent. Precautions in the preparation of Grignard reagents. During the preparation of Grignard reagent, the following precaution must be observed. First, the apparatus should be perfectly dry and protected from moisture by using a calcium chloride guard tube. Second, all the reagents and solvents, that is alkyl or aryl halide, magnesium metal and ether must be absolutely dry. Third, ether used as solvent must be completely free from alcohol. This can be done by first washing ether several times with water, followed by drying over anhydrous calcium chloride for 1 to 2 days and subsequent distillation over sodium. Fourth, an atmosphere of dry nitrogen should be maintained throughout the course of the reaction. These precautions are necessary since Grignard reagents are decomposed by moisture and react with oxygen and carbon dioxide to form alcohols and carboxylic acid respectively. The ethereal solution of Grignard reagent thus obtained is generally used as such for various reactions by adding it to the other reagents. Mechanism. The mechanism of the formation of Grignard reagent is still not certain. According to Gomberg and Beckmann, the reaction commences with the formation of a small amount of magnesium halide and then proceeds by a free radical mechanism. This mechanism also elegantly explains the initiating effect of iodine, which may be ascribed to the formation of magnesium iodide from magnesium and iodine. 2.2.2 Structure of Grignard reagent. The structure of Grignard reagent has not been finally settled so far. The recent research has shown that the actual structure varies with the particular Grignard reagent and the solvent used for its preparation. Grignard and Blase observed that evaporation of ethereal solution of Grignard reagent resulted in a white solid having the composition RMgX.2C2H5 They suggested that ether molecules were present as ether of crystallization. X-ray analysis of these dietherates suggests that the four groups are arranged tetrahedrally as shown in Formula 1. Thus, Formula 1 suggests that ether does not merely provide a medium for the reaction, but it also helps to dissolve the Grignard reagent formed due to solvation by ether molecule. This is supported by the observation that Grignard reagents can be prepared even in benzene solution in presence of a tertiary amine which coordinates with magnesium like ether and thus dissolves it. Further, Formula 1 shows the Grignard reagent in the monomeric form, but physical studies have revealed that Grignard reagent exists as a 1:1 complex of a dialkyl or diaryl magnesium and magnesium halide coordinated with molecules of ether. These two species are held together by halogen bridges as shown in Formula 2. However, for the sake of convenience, the formula RMgX has been used to represent alkyl magnesium halides in the text. 2.2.3 Reactions of Grignard reagents. The carbon-magnesium bond in Grignard reagent is highly polar due to large electronegativity difference between carbon and magnesium. Consequently, due to greater electron density around carbon, the alkyl group in Grignard reagent can act as a carbanion or a nucleophile, that is, it can attack any electron deficient center in other molecules. In other words, Grignard reagent chiefly undergoes nucleophilic substitution or nucleophilic addition reactions. First, nucleophilic substitution reactions. Grignard reagents react with compounds containing an active hydrogen or halogen atom. All such reaction involves the nucleophilic attack of the alkyl group of the Grignard reagent on the electron deficient center as shown below. That is, RMgX plus AB gives Ra plus MgBx. Second, nucleophilic addition reactions. Grignard reagent react with compounds having a multiple bond such as carbonyl, C double bond S, nitrile, etc. to form addition products which when hydrolyzed yield a vast variety of compound. In all such reactions, the addition of the nucleophilic group of RMgx, that is R negative, occurs at the most electropositive end, and that of MgX group at the more electronegative atom of the multiple bond. Thus, carbonyl group plus Grignard reagent gives addition product which on hydrolysis gives an alcohol. 2.2.4 Synthetic uses of Grignard reagents. Grignard reagents serve as extremely valuable starting material for the synthesis of a vast variety of organic compounds. They have attained a position in synthetic organic chemistry unrivaled by any other class of compound. To illustrate this, some important synthetic applications of Grignard reagents are described below. First, alkanes. By action with active hydrogen containing compound. Active hydrogen containing compounds such as water, alcohol, thioalcohols, carboxylic acid, hydrogen sulfide, ammonia, amines, terminal alkynes, etc. react with Grignard reagent to form an alkane corresponding to the alkyl or the aryl group of the Grignard reagent. RMgX plus Hb gives RH plus MgBx, where B is hydroxide group OR, SR, OCOR, NH2, NHR, NR2, etc. For example, methyl magnesium iodide plus water gives methane plus MgOHI. Since methane is evolved quantitatively when CH3MgI is treated with compounds containing active hydrogen, therefore these reactions can be used for the estimation of OH, NH2, SH groups in organic compounds. The method employed is called Zerivitinov's method. Aryl magnesium halides also behave in similar manner. For example, phenyl magnesium bromide plus water gives benzene plus MgOHBr. Second, by action with reactive alkyl halides. Grignard reagent react with reactive alkyl halides such as T-butyl chloride, benzyl chloride, etc. to form alkanes. That is, methyl magnesium iodide plus tertiary butyl chloride in reaction with dry ether give neopentane plus MgICl. Ethyl magnesium bromide plus benzyl chloride in dry ether gives 1-phenyl propane. Second, alkenes. Grignard reagent being weak nucleophiles do not react with simple alkyl halides. However, compounds containing more reactive halogens such as allyl iodide, etc. react with them, giving alkenes. For example, allyl iodide plus methyl magnesium iodide gives 1-butane. Third, alkynes. Grignard reagent react with terminal alkynes forming alkynyl Grignard reagents which upon treatment with alkyl halide give higher alkynes. For example, propyne plus methyl magnesium iodide gives propionyl magnesium iodide. Fourth, primary alcohols. By action with ethylene oxide followed by hydrolysis. Grignard reagent react with ethylene oxide to form addition product which on hydrolysis will dilute hydrochloric acid from primary alcohols containing 2 carbon atom more than the alkyl halide. Ethylene oxide plus Grignard reagent give addition product which upon hydrolysis gives 1 degree alcohol. For example, phenyl magnesium bromide plus ethylene oxide gives 2-phenyl ethanol. Second, by action with formaldehyde followed by acid hydrolysis. When treated with formaldehyde, Grignard reagent forms an adduct which on hydrolysis with dilute hydrochloric acid gives a primary alcohol. C. By action with oxygen. Primary alcohols are formed by passing dry oxygen through the solution of a Grignard reagent followed by acid hydrolysis of the resulting addition product. Fifth, secondary alcohols. A. By action with aldehyde other than formaldehyde followed by acid hydrolysis. Aldehyde on reaction with methyl magnesium iodide gives CH3CHCH3OMgI which upon hydrolysis gives isopropyl alcohol. B. By treating an excess of a Grignard reagent with ethyl formate. The reaction takes place in 2 steps. Grignard reagent first react with ethyl formate to form an aldehyde which in turn reacts with another molecule of Grignard reagent to yield an adduct which forms a secondary alcohol on hydrolysis. 6. Tertiary alcohols. First, by action with ketones followed by hydrolysis, that is ketone on reaction with Grignard reagent and upon hydrolysis gives 3-degree alcohol. Second, tertiary alcohol having a least two similar alkyl group may be prepared by the interaction between an ester other than formic ester and an excess of Grignard reagent. The reaction proceeds in 2 steps. Third, by reaction with acid chlorides and anhydrides. Grignard reagent react with acid chlorides or anhydrides to give addition product which upon acid hydrolysis gives tertiary alcohol. The reaction takes place in 2 stages. 7. Ethers. Grignard reagent react with lower halogenated ethers to yield higher ethers. 8. Aldehydes. A. When a Grignard reagent is treated with ethyl formate, an aldehyde is formed. However, with excess of Grignard reagent, the product obtained is a secondary alcohol. B. Aldehydes are obtained in a better yield if ethyl orthoformate is employed instead of ethyl formate. This is so since the formation of acetal in the case prevents the formation of secondary alcohol. C. Aldehyde may also be obtained by the interaction between a Grignard reagent and hydrogen cyanide followed by hydrolysis of the adduct formed. 9th. Ketones. A. By treatment with alkyl cyanides followed by acid hydrolysis. For example, acetonitrile plus ethyl magnesium bromide gives the CH3C double bond and MgR and CH2CH3 which on hydrolysis gives ethyl methyl ketone. B. By action with acid chlorides. As discussed on page 83, equimolar amounts of a Grignard reagent and an acid chloride give an addition product which form ketone on hydrolysis. If Grignard reagent is used in excess, tertiary alcohols are obtained as ultimate products of the reaction. 10. Monocarboxylic acid. Grignard reagents interact with dry ice to form addition product which on acid hydrolysis give monocarboxylic acids. 11. Esters. By action with ethyl chloroformate. Equimolar amounts of Grignard reagent and ethyl chloroformate react together to form higher esters. 12. Thioalcohols. Grignard reagent react with sulfur to give an addition product which gives a thioalcohol on hydrolysis. 13. Phenols. Aryl magnesium halides react with oxygen to form addition product which upon hydrolysis gives phenol. 14. Alkyl cyanides. By interaction of Grignard reagent and cyanogen chloride or cyanogen. Excess of Grignard reagent is avoided since it will react further with alkyl cyanide to yield ketones. 5th. Primary amines. Grignard reagent react with chloroamine to form primary amines. Reasonable yields of primary amine is obtained only with Grignard reagent containing tertiary alkyl group. Primary amines can also be prepared in satisfactory yield by the action of a Grignard reagent on orthomethyl hydroxylamine. 16. Sulfuric acid. On passing sulfur dioxide into a well-cooled solution of Grignard reagent, an addition product is obtained which on hydrolysis gives sulfuric acid. 17. Dithioic acid. These are prepared by the action of Grignard reagent with carbon disulfide followed by acid hydrolysis. 16. Organometallic compounds. Grignard reagent and inorganic halides interact with each other resulting in the formation of other organometallic compounds. 2.2.5 Abnormal addition of Grignard reagents. First, addition to hindered ketone. If the Grignard reagent or the ketone contains branching at the alpha carbon, sometimes the usual addition reaction does not occur due to steric hindrance. Instead, reduction occurs in which a hydride ion is transferred from the Grignard reagent to the ketone via a 6-membered cyclic transition state in a manner similar to Marvin-Pondrow-Verley reduction. For example, when isopropyl magnesium bromide is added to diisopropyl ketone, then expected 3-degree alcohol is not formed. Instead, the secondary alcohol, diisopropyl carbinol, is obtained by reduction of the keto group. Second, addition to alpha-beta unsaturated compounds. Alpha-beta unsaturated carbonyl compounds react with Grignard reagent to form 1,2 and 1,4 addition product. The orientation of addition is often controlled by steric factors. In general, substitution at the carbonyl group favors 1,4 addition, while substitution at the double bond favors 1,2 addition. For example, 1,2,3 triphenyl prop 2 in 1 on reaction with phenyl magnesium bromide and hydrolysis gives 1,2,3,3 tetraphenyl propane 1 on. In most cases, both products are formed, but alpha-beta unsaturated aldehydes nearly always give exclusively 1,2 addition products when treated with Grignard reagents. However, the extent of 1,4 addition of Grignard reagent can be increased by carrying out the reaction in presence of cuprous chloride or cupric acetate, etc. This is called conjugation addition and probably occurs by a free radical mechanism. 2.2.6 Limitations of Grignard synthesis. Grignard reagents suffer from the following limitations. First, Grignard reagents are sensitive to moisture, oxygen and carbon dioxide and hence must be protected from them. This makes the handling of Grignard reagent difficult. Second, Grignard reagents cannot be prepared from alkyl halides containing other reactive functional group such as OH, SH, NH2, carboxylic, SO2, aldehydic ketone, ester, cyanide, etc. since all react with them. Only alkyl halides containing a few other groups such as R, OR, AR, X can be used to form Grignard reagents. Third, generally branching of the carbon chain near the functional group prevents reaction, probably due to steric hindrance. For example, CH3-MgBr or CH3-MgI does not react with ditert butyl ketone. Similarly, if the Grignard reagent contains large alkyl groups, the reaction is sometimes prevented again due to steric hindrance. For example, isopropyl methyl ketone reacts with CH3-MgI but not with tert butyl magnesium chloride. Fourth, compounds which are capable of enolization liberate hydrogen with Grignard reagent. Fifth, nitro compounds cannot be used in Grignard synthesis since they oxidize the Grignard reagents. Despite the above limitations, Grignard reagents are still the most important tools in organic synthesis. 2.3 Organozinc compound. Although organozinc compounds of the type R2ZN are not commonly used in organic synthesis, they are particularly useful when milder reagents are required. 2.3.1 Methods of formation. Following methods have been used for the preparation of organozinc compound. First, from alkyl halides. Alkyl iodides react with zinc-copper couple in high boiling ether to form alkyl zinc iodide, which upon subsequent distillation in an atmosphere of carbon dioxide undergo disproportionation to give dialkyl zinc compound. That is, ethyl iodide plus zinc gives 2C2H5ZnI, which upon distillation gives diethyl zinc plus ZnI2. Second, from organoaluminium compounds. Treatment of trialkyl aluminium with zinc chloride gives dialkyl zinc compound. This method formed the basis of laboratory preparations of these compounds. 2.3.2 Physical properties. Dialkyl zinc compounds have linear geometry due to sp hybridization of zinc atom. They are non-polar, low boiling points and or low melting solids soluble in organic solvents. The lower zinc compounds are highly inflammable in air and hence are usually prepared and used under carbon dioxide atmosphere. 2.3.3 Chemical reactions. The chemical reactions of organozinc compounds are similar to those of the Grignard reagent, with the only difference that they are less reactive. For example, they do not react with carbon dioxide and react only slowly with cyanides, ketone and esters. Some important chemical reaction of dialkyl zinc compounds are discussed below. First, reaction with water. They readily react with water, forming alkanes. Second, reaction with alkyl halides. Dialkyl zinc compounds do not react with 1 and 2 degree alkyl halides. They react only with 3 degree alkyl halides to form alkanes containing a quaternary carbon atom. Third, reaction with acid chlorides. They react readily with acid chlorides to form ketone. For example, diethyl zinc plus acetyl chloride gives out butanone. Ketones are obtained in good yields because dialkyl zinc compound react very slowly with them. Third, Reformatsky reaction. When an aldehyde or a ketone is added to a solution of an alpha haloester in presence of zinc, an organozinc compound is first formed, which then adds to the carbonyl group in a manner similar to the Grignard reagent to form a beta hydroxy ester. This reaction is called Reformatsky reaction and is useful method for preparing beta hydroxy esters or acids and their derivative. 2.3.4 Iodomethylene zinc iodide. Iodomethylene zinc iodide is an important organozinc compound as is obtained by the action of Zn copper couple on methylene iodide. It reacts with olefins to form cyclopropane derivative. This reaction is called Simon-Smith's reaction and is used for preparation of cyclopropane derivative. The addition occurs in a stereospecific syn manner according to the following concerted mechanism. That is cis-2-butane on reaction with CH2ZnI2 gives transition syn which upon gives cis-1,2-dimethyl cyclopropane. 2.4 Organolithium compounds. Compounds in which lithium atom is directly bonded to a carbon atom are called organolithium compound. For example, methyl lithium, ethyl lithium and butyl lithium, phenyl lithium. Organolithium compounds are more reactive than Grignard reagent and also undergo a few additional useful reactions. Therefore, they are widely used in organic synthesis these days. 2.4.1 Formation of alkyl lithiums. First, by action of an alkyl halide with lithium. Alkyl lithiums are generally prepared by treating an alkyl halide with lithium in hexane, benzene or any other hydrocarbon solvent at a low temperature in an inert atmosphere of nitrogen or argon. That is, methyl bromide plus 2 lithium in dry hexane gives methyl lithium plus lithium bromide. Ethyl bromide plus 2 lithium in dry hexane give ethyl lithium plus lithium bromide. For the preparation of alkyl lithiums, hydrocarbon solvents are preferred over ether since the use of ether not only encourages Wurtz reaction but also reacts with it. Diethyl ether plus N-butyl lithium gives butane, which again on reaction with lithium compound gives ethylene. Second, by metal exchange. Alkyl lithiums can be readily prepared by the replacement of one metal by another. 2.4.2 Chemical reactions of alkyl lithiums. The carbon-lithium bond is more polar than carbon-magnesium bond. Therefore, alkyl lithiums are more reactive than the Grignard reagent. Except a few differences, their chemical behavior is similar to that of Grignard reagents. Some of their important chemical reactions are discussed below. First, resemblance with Grignard reagent. They resemble Grignard reagent in most of their reactions. Some of these reactions are: first, formation of hydrocarbons. Like Grignard reagent, they react with compounds containing active hydrogen to form the corresponding hydrocarbon. For example, methyl lithium plus water gives methane. Second, formation of primary, secondary and tertiary alcohol. A. Primary alcohol by action with formaldehyde. Formaldehyde plus alkyl lithium gives addition product which upon hydrolysis gives 1 degree alcohol. Like Grignard reagent, alkyl lithium compounds also react with ethylene oxide to form primary alcohol containing 2 carbon atoms more than the starting alkyl or aryl halide. B. Secondary alcohol by action with aldehyde other than formaldehyde. Acetaldehyde on reaction with methyl lithium gives a addition product which upon hydrolysis give isopropyl alcohol. C. Tertiary alcohol by action with ketones. Acetone plus methyl lithium gives addition product which upon hydrolysis gives third butyl alcohol. Third, formation of ethers by action with the monochloroether. Fourth, formation of aldehyde by action with ethyl orthoformate or hydrogen cyanide. That is, hydrogen cyanide plus methyl lithium gives addition product which upon hydrolysis give acetaldehyde plus ammonia plus LiOH. Fifth, formation of ketone by action with any orthoester other than orthoformaric ester or alkyl cyanide. Sixth, formation of nitriles by action with cyanogen chloride. That is, methyl lithium plus cyanogen chloride gives acetonitrile plus lithium chloride. First, reaction with alkyl halides. Alkyl lithiums react with alkyl halide to form alkane. For example, ethyl lithium plus methyl bromide gives propane plus lithium bromide. Phenyl lithium plus ethyl bromide gives ethyl benzene plus lithium bromide. 7. Reaction with aryl halides. Aryl halides undergo nucleophilic substitution reaction by elimination, addition or benzene mechanism. 8. Reactions with heterocyclic compound. Heterocyclic compounds undergo nucleophilic substitution reaction by bimolecular displacement mechanism. For example, pyridine on nucleophilic aromatic substitution gives 2-phenylpyridine plus lithium hydride. Second, difference from Grignard reagents. Organolithium compounds, being more reactive than Grignard reagent, undergo some additional reactions as discussed below. First, action with carbon dioxide. Grignard reagent yield carboxylic acid with carbon dioxide, while organolithium compounds yield ketones. That is, carbon dioxide plus RLI gives out an addition product which upon hydrolysis gives ketone. This difference is due to the reaction that organolithium compounds are more strongly nucleophilic than Grignard reagent and thus react further with the intermediate resonance stabilized carboxylate anion giving ketones. Second, action with carboxylic acid. Alkyl lithium compound react with carboxylic acid yielding ketones as the main product. Grignard reagent on the other hand give alkanes corresponding to the alkyl group of the Grignard reagent. Third, addition to a carbon-carbon double bond. Unlike Grignard reagent, organolithium compounds add to simple alkenes to give a mixture of compound. The addition occurs at a high pressure. Fourth, formation of tertiary alcohol. Organolithium compound, being more nucleophilic and smaller in size than the corresponding Grignard reagent, add to sterically hindered ketones to form sterically hindered tertiary alcohol. Grignard reagent on the other hand do not give such addition reaction. For example, isopropyl lithium adds to diisopropyl ketone to yield triisopropyl carbonyl. In contrast, when isopropyl magnesium bromide is added to diisopropyl ketone, the expected tertiary alcohol is not formed. Instead, reduction of the ketone by the Grignard reagent occurs to give diisopropyl carbonyl and propylene. Next, fifth, reaction with alpha-beta unsaturated carbonyl compound. Organolithium compounds, being more nucleophilic, predominantly undergo 1,2 addition to alpha-beta unsaturated carbonyl compound, whereas Grignard reagents give mainly 1,4 addition products. Thank you.